when designing our controllers for successive loop control design, we used proportional integral, proportional derivative controllers, as well as a filter. So in this lecture, what we're going to do is talk about implementation details for both the PID and for that filter. So let's go ahead and get started. As we jump in, now we're going to assume that E is some generic error, right? We have a generic error signal that we're going to be using for design of our PID loop. Now we used both PI and PD, and so that's just different components for what we have here. So again, if we had PI, it would be these two components. If we had PD, it would be these two components. And if you used all three of them together, then you're good to go. Okay, so we have our control laws, and we have our error signal. So if we take the Laplace transform of that, what we're going to end up getting is we'll have the 1 over s, right? 1 over s is equal to an integral. And we'll multiply by s for our derivative. Now that derivative is going to amplify a noise. And so you really don't want to have a derivative, a straight up derivative in your PID control. So what you can do is just use a band limited differentiator. So in this case, this is almost like this is our band limited differentiator. It's basically, this is a low pass filter with the differentiator. So we low pass filter our derivative, but then we're good to go. And so this is parameterized by that value tau. Excellent. So that's now in the Laplace domain, and we have this continuous time representation. But when we go to implement it, it's going to be implemented in a discrete fashion, right? We have a digital computer that we're going to be implementing these things on. One other note to make is that if we do our differentiating in the derivatives that we used, we still have our derivatives. In the PD controllers we developed, used a derivative that was one of the states. So if you already have one of the states defined, then there's no reason to try to numerically differentiate. So in other words, no need for a numerical derivative. Okay, so keep that in mind. So we already had the derivatives for us. We don't need to design this band limited differentiator. Okay, although we do use one on the yaw filter. Okay, so now let's talk about implementation. Right, we're going to use the trapezoidal rule. Oops, I thought I had my highlighter. We're going to use the trapezoidal rule for converting from continuous time to discrete time. So we're going to convert our s to this value where we have that trapezoidal rule. Now when we use our integrator, just note that this is 1 over s. So this guy right here is the inverse of the s value that we see above. So anytime we have an integral, we are going to add in the 1 over s. If we're differentiating, we have the s. So anywhere we see s, we'll put those things in. Okay, so if we look at in the z domain, so this is in the z domain, our discrete frequency domain, right? We'd have our integrator is going to be designed as this trapezoidal rule times our error, right? as we convert that to the discrete time domain, so we have a discrete time domain representation, our integrator is going to be the integrator at the previous value, plus, now this is where the trapezoidal rule really comes in. We have our sampling time over 2. We have the current error, and we have the previous error. So one thing to note is that we need to keep the previous integral and error in memory. Okay, so we keep the previous integral and the error value for our integral and the error in memory. So these two values. Excellent. So then our differentiator term, it's going to be very similar to what we did before. We're just plugging in s every time we see our s value, right? So we have our s divided by tau over s plus 1. So this is just our s. And so we have tau over s plus 1. And then we can look at the resulting value for it. So this is again in the z domain. And this is in the discrete time domain. Okay, so now we see that we take our derivative from so we still do our derivative from our previous value, and we are going to multiply it by the scaling factor. And then we have this, again, we have our trapezoidal rule giving us that we have to have the error from our previous time value as well. So again, we need to store previous derivative value and the previous error. So that's these two terms. So we need to keep that in memory so that when we see the new error, we can take the difference between it, use that, and that'll help us with our trapezoidal rule, and plus our low-pass filter. And we also take a look and the low-pass filter comes into play in terms of not letting us, or we take the previous derivative value into play in our low-pass filter as well. Excellent. So we can define our integrator and our differentiator, and we can discretize them really nicely. Okay. Another thing we have to worry about is integrator windup. So to provide some motivation, assume that I have a desired value that I'm trying to get to, right? And even when I have when I'm starting at 0, so I'm given a step response, I'm going to be putting in as much control authority as I can, right? So here's the response to our system, and we're going to end up overshooting, right? Well, in the interval all the way from here, we're going to be taking our integral term is going to be adding all this up, right? So it's going to be calculating the area under our error bar, or between our actual and desired. So it's going to be summing up that error, and this actually causes some of that overshoot. And so we have to do the negative value over here, and we'll pull in, and so the integrator adds oscillation. Well, in reality, right, what we care about the integrator for is, oh, I did black there, is that our nominal response might have a steady state error, right? So we really only care about the integral contribution we only care about, oh, if I draw it, we care about the integral contribution here, right? So we want to try to get rid of, and I'll use that black, we want to try to get rid of that component, or at least part of it. So we don't want our integrator to wind up so much, right? We want it to be down here using this component to get rid of steady state error, but not building up the integral as we're shooting towards the desired value. So that's just some motivation there. So let's talk about this. There's a host of different ways to do anti-integrator windup, and this is just one decent way. So we come in here, and the first thing I'm going to mention is notation. Oh gosh. We use the superscript plus to denote after update. And the minus is before an update. Oh my gosh, I cannot write. Okay, let's try that one more again. One more time. Before update. Note that these are both at the same time instance. So we're just saying, hey, at the same time instance, oh gosh. We're going to rewrite that just because we should. So they're both at this correspond to the same time or moment in time. I don't know if that was much better. Okay, they both correspond to the same moment in time. It's just one is before an update and one is right after an update. So this value right here, we're going to call this our U unsaturated. So we have U unsaturated with the minus, right, to denote no update yet. Okay, so this equation, I'm going to call equation 1. This is our standard PID loop, right, or PID control. So we've just calculated our control, but then we have to actually saturate our control. Our control, we're not allowed to give an infinite amount of control, so we're going to end up saturating it. So this equation 2 is after the update. And what we're going to do is we're going to have our integral before and our integral after. Now, I want to clarify something right here. We don't actually calculate our U unsaturated like this. What we do is, 1, we'll use equation 1 to calculate our control. And then 2, we're going to saturate our control. And we'll just allow our actual control to be equal to a saturation function where we say, hey, if we're below some, well, let me write it down. So we'll do our U unsat. How did I write that? Unsat, yeah. Minus. And then we're going to do a lower bound and an upper bound. So what this function does is that if U is in, oops, sorry, if U unsaturate, well, let's just write it out here. So we'll say that this does just a case statement, right? So U is going to be equal to the lower if U unsat minus is less than the lower. It's going to be equal to U unsat minus if the lower is less than or equal to u unsat minus is less than or equal to high, and then we'll say that it's going to be the high value for u unsat minus is greater than the high value. Okay, so we have this saturation function. We're going to saturate our input. Okay, so we have this saturation function, and that's how we calculate our control. This is and when I say this, 3, we're then going to apply the control. So that's the control we end up using. We saturate it. We have not cared anything about anti-windup yet. Okay, but we want to know how much we should basically wind down our integral based on the saturation. Okay, so we have this second equation, and this is actually just equal to our u. So this is the u that we apply. And we're going to pretend like we calculated it like this. So we want to know what is the actual integral term that we ended up using. So we're going to define this integral plus is equal to the integral minus some plus some delta I. Okay, so below this line, all we're doing is we're going to calculate this delta I. Okay, so we have if we look at equations 1 and 2, so from 2, we can say that U unsaturated plus is just equal to U unsaturated minus, and then we're going to, we don't have this final term, so we'll subtract off minus Ki I minus, and we'll do plus a Ki I plus. So that's how we end up getting to this term. And then we use this relationship where delta I is just going to be equal to I plus minus I minus. Excellent. So now we let our U unsaturated equal to our U. So again, we've actually saturated our control. Okay, and then what we do is we say, well, the question here is, what is this delta I? What is the change? What's the difference we've actually done there? So we say, hey, this delta I is equal to 1 over K I times U minus U unsaturated. And that's just by solving for this equation, right? So we now solve for our delta I, and we get this relationship right here. So we'll then update our integral. So before we finish this control loop, we'll say let's take off some of our integral. And so we'll update our integral, say this is the integral we calculated using our normal techniques, and then we're going to remove this component, this amount, from the integral. And this helps us not wind up as we're saturating our control. Okay, excellent. Now we'll jump into our yaw damper implementation. And the yaw damper is just implemented as, we just have this transfer function that takes us from the output to our input, right? And one thing that I want you to note is that our control is very similar to this transfer function where we have K times TS times S all over TS times S plus 1. So that's what we're using for our yaw damper implementation. So in other words, this guy is equal to 0, this guy is equal to 1, tau sub S, and this guy is equal to 1. Did I do that right? Oh, I guess we could switch out our k and our, I think we could have our k times that is equal to 1. So we can do either one. Not equal to 1, but tau sub s. Okay, so we want to be able to calculate the equivalent discrete time transfer function. Again, we use the trapezoidal rule, and all we're doing is we put in s, whoops, not for b naught. We do s's every time we see, sorry, we use our trapezoidal on this guy, and the goal is to get some h of z. And then, so once we plug in that value for s in the original continuous time transfer function, we can do all the math to simplify. And originally the slide had a k in front of the a1 term, shouldn't have that k. And then we can go through and just as we've done before, we can then pull it off into discrete time. And we can apply that control there. So the way well, I won't go into the details on that. So we just can take the input u that we're getting, and it's just going to be based on the previous input and the current value for y and the previous value for y. So that's our y damper implementation. Here's the actual implementation. The one difference that this one has is that you can just multiply by 1 over tau sub r and divided by 1 over tau sub r, right? So multiplying by 1, but basically then we get this p w naught is just equal to 1 over tau sub r. Okay, so you can rewrite it in slightly different form. And this is just the resulting transfer function that you would get in implementation if you'd have these values. Okay, excellent. So that's all those are some implementation details to help us out. Again, all we did for the most part was 1, we just plugged in our trapezoidal rule every time we saw an s. 2, we low pass filtered our derivative, and 3, we looked at our integrator and we tried to make sure that we didn't have, or we tried to negate some of the effect of the integrator wind up.